The purpose of this lecture is to show how to write a gradient operator in different coordinate systems, including curvilinear coordinates like polar coordinates or spherical coordinates. For this, we will need some theory. First, imagine that you want to solve some simple textbook problem in physics. What do? You usually start with choosing coordinates. It means that in your physical space you choose an origin, one point, usually somewhere in the middle of your problem, and then you choose a basis. A basis can be positioned also in such a way that it fits your problem. I have positioned my EX vector and EY vector as it is shown on the blackboard. I have done it in a special way. In particular, those two vectors are orthogonal. What this means from the theoretical point of view? From the theoretical point of view, it means that my physical space is an affine space, A. Affine space is very similar to vector space, but the origin is not distinguished. So there is no distinguished zero vector. However, from one point to another point of an affine space, I can move using vectors. This of course means that affine space is not just one set, but I have also a vector space, which is usually called a model vector space. To be mathematically precise, let me write a definition. What is an affine space? An affine space is a set together with a vector space and together with a certain operation. The operation acts from pairs of a point in the set and a vector gives us another point in the set, and there are certain conditions. The first condition says that if I move from the point A by the vector v and then from the resulting point by the vector w, this is the same as moving from the point A by vector v plus w. The second condition says that if I move by the vector 0, nothing changes. And the third condition says that for all pairs of points there exists just one vector, such that if I move from point A by this precise vector, I get B. So this is very abstract. Usually we write it in a very different way. So instead of this alpha, we use plus sign. Then the first condition says that A plus V and then plus W gives the same as A plus VW. The second condition says that A plus 0 vector is A. And the third condition is that for all AB, there exists, for every pair AB, there exists just one vector V, such that A plus V equals B. Let me come back to my basic vectors for a while. The fact that I was able to position them in such a way that they are orthogonal means that I know what does it mean they are orthogonal. It means that in my model vector space I have a scalar product. So V is not just V, but V with scalar product. Such a triple affine space with vector space and scalar product is usually called an affine Euclidean space. Let us move on. We have defined our origin and we have defined our basic vectors. This means that we have identified our affine space with Rn. Now in our case on the blackboard we have identified our space with R2, and we have done it in such a way that it is compatible with the structure of our initial affine space. However, in some situations, in some physical situations, it is really not very convenient to use such coordinates that come from orthonormal basic vectors. Sometimes we would like to do it in a very different way. I have prepared some pictures. This is one of the pictures I want to show at the moment. On this picture there is an affine space A identified with R2 with using basic vectors that are not orthogonal. We can compare it with another identification which is done with vectors that are orthogonal. I'm sorry, I do not control those pictures very well. Okay, so here we have a basis. Vectors are not orthogonal. However, still we have coordinates, and here we have a basis. Vectors are orthogonal, and this is something we are more used to use. Formally, what is the coordinate system? Coordinate system is a map. Again, what do we do formally? Formally, we have defined a map. We have defined a map F coming from some open subset of Rn with values in A, and this identifies a piece of A with a piece of Rn, and the map is as follows. There is a chosen point A plus coordinates multiplying our basic vectors. If we have n basic vectors and everything is n-dimensional, it looks like that. And this is the value associated with coordinates. This is our F. Of course, in our case n equals 2. Instead of numbers here we use x and y, and we identify x and y with a point plus x ex y ey. And if ex ey are orthogonal, it looks more like that. If they are not orthogonal, it looks more like that. Such coordinates are called affine coordinates because they are adapted to the affine structure of the space. Moreover, they can be defined for all Rn, not for some subset, but for all Rn. Because this formula makes sense for any set of any coordinates x1 to xn. From now on, we will assume that we have already done this. It means we have identified our affine space with Rn, and we will be working with Rn in the following. If our physical problem has some symmetry, for example rotational symmetry, we may need another coordinates which are not affine and which are not adapted to the structure of the affine space. For example, for n equal 2, we may need polar coordinates. How are they defined? Probably everybody knows. We have a map from a Cartesian product of two intervals. One of them is very long, another is shorter. The elements are r and phi, and they are mapped to r times cosine of phi, r times sine of phi. Let us look at the picture. We have Cartesian coordinates, I mean those orthonormal coordinates, and on them I have drawn coordinates associated to this map. R changes along green lines, phi changes along blue lines. This is probably something you know very well. This map is not defined on the whole R2, but indeed on some open subset, and the image is also not in the whole A, which we consider identified with R2, but in some open also open subset. In this case, this open subset is R2 without the origin and without positive x-axis. Now we can start to differentiate functions. Imagine we have a function which is defined in the neighborhood of point P here. This is a function of two variables with values in R. To differentiate it, I move a little bit from the point P, so I consider f at P plus h, where h is some tiny displacement, and what I get is f at point P plus the differential acting at this displacement h, and the rest. The rest depends on P and on h. And this is small, and this is a linear map. A linear map from R2, here are those displacements, to R. As a matrix, I can write this linear map as a matrix, provided I have a basis. Of course, if I have coordinates, I have a basis. Here on this picture, I have those EX and EY. So I consider this map a matrix. From basis A to also some bases in R, but R is a very simple vector space with distinguished bases being number 1. What are the matrix elements? The matrix elements are partial derivatives df over dx, df over dy. So the derivative, being a linear map, acts on the displacement vector in the following way: df dx, df dy acts on h, which is also written in this basis, so it consists of the displacement in the direction of x and the displacement in the direction of y. This is my h written in basis e, and the action is usual: df dx multiplied by delta x, df df dy multiplied by delta y. Let us notice that in this formula no coordinates are used. This is the point when I differentiate. This is the displacement. This is the linear map. Every objects are abstract objects. If I have a rotational symmetry of my problem, this basis is not really useful. I will probably want to write this, and especially the differential, in different coordinates. For example, in polar coordinates. Let us look for an appropriate picture. It is definitely somewhere there. Oh, it's here. Let's move it to the right place. Okay. Our orthonormal Cartesian basis is here, and it is not adapted to polar coordinates. We would rather like to use such basic vectors that change along the coordinate lines. Those particular vectors are chosen in such a way that they are orthogonal and they have length 1. So this is an orthonormal basis, however rotated a little bit, and it is easy to write the appropriate formulae for those two basic vectors. And this vector gr is cosine phi times ex plus sine phi ey, and vector g phi is also rotated minus sine phi ex plus cosine phi ey. So I have a definition of new basis, and I can write my differential of a function in basis g. How to do it? I have to apply a matrix of the matrix that changes the basis. I take the matrix I know in basis E, and I multiply by identity as a linear operator, but acting from basis G to basis E, and this is precisely the rotation matrix. So the result is as follows. Here I have df dx, df dy multiplied by the matrix, and what is the result? The result is the following. Cosine multiplies because as usual I multiply row by column, row by column. So df over dx plus sine phi df over dy, and the second component of the matrix is minus sine df dx plus cosine df dy. However, it is not what I really wanted, because here and here and here and here I have something which is associated with old coordinates x and y, and I want in this whole thing new coordinates, but so expressions that are associated with phi and r, or rather, if I want to keep it in correct order, with r and phi. How to get rid of x and y? Now we have to do the following. Our function is from r2 x y to r. We can compose it with our coordinates phi that come from 0 plus infinity times 0 to pi, and we can consider this function, the composition f composed with phi. This has arguments r, and phi, and reads f of x of r and 5 and y r and phi. Therefore, this composition differentiated by r, we will use the same symbol f instead of f composed with phi, because this is the accepted convention. So the f over the r is the f over the x, and then the x over the r, which is cosinus phi, plus the f over dy and dy over the r, which is sine phi. And we recognize that what we have obtained here is here. Then the second coordinate phi, the f over the phi, and again the f over the x, and then we differentiate x with respect to phi, so we get r minus sinus phi plus the f over dy and dy over the phi, which is r cosinus phi. Do we have the same here? No, we don't. There is a difference. A slight one, but still important. The difference is here. Here we have r, here we have r, and here we don't have this r. We can continue here with our calculations, writing that this previous matrix is equals df dr and 1 over r df d phi. Recall that this is a matrix of the differential of our function in the basis g, from g to 1. And what would it be such a matrix? What's that? Does it have anything to do with the differential of function f? Of course it does. However, it is a matrix written in, again, different bases. The difference is in the second component of the basis. The basis G was a basis composed of GR, G phi. Both were of length 1 and they were orthogonal. The picture. Probably it is better to recall the picture. The picture is here. Let's move it here. Yeah, this is the picture. Now we will need such a basis where this matrix element is a component of a differential with this base, with this new basis. This new basis will have to have a different vector, the different second vector, and this different second vector will be multiplied by r. So this new basis will be composed of gr and rg phi. So what's that? How do I guess it? For this I need another picture. Imagine I have a polar coordinate system and I consider two curves. One is a curve that goes along r coordinate and changes in such a way that phi is constant and r coordinates changes with t. So t runs this way, have a 0 point here, and when I when I look for a tangent vector, which means I differentiate the coordinates with respect to t, what I get is in Cartesian coordinates cosinus phi times basic vector ex plus sine phi times basic vector ey. So what I get is precisely gr. This is a vector which is tangent to coordinate curve when the parameter of the curve changes in the same way as coordinate changes. But if I do the same for coordinate phi, so I consider this curve and I change phi, what I get is the following vector: r minus r sinus phi ex plus r cosinus phi ey. So this is the second vector of the new basis that I need. This is the vector tangent to the coordinate curve, and the parameter of the curve changes in the same way as coordinate changes. There is a very convenient notation for those two vectors. This will be denoted by dr and this will be denoted by d phi. Why such a notation? Precisely because those vectors correspond to differentiation with respect to coordinates of this new coordinate system. So I can come back to my calculation and write that this is a matrix of my differential, with the basis d phi here, and this distinguished by basis in r equal to 1. Okay, so this was a very lengthy introduction to the main problem, the main question, which is a question of the gradient. Let us summarize what we know. We have two coordinate systems, x, y, and r phi. We have basic vectors corresponding to this system, and we have two sets of basic vectors in a sense corresponding to polar system, which is gr g phi and dr d phi. These are orthonormal. These are orthonormal. But these are not orthonormal, they are only orthogonal. The length of dr is 1 because this is the same as gr. However, the length of d phi is r, and d phi is r times e phi. So this is our starting point. And we can now come finally to the gradient. What is the gradient? The gradient is a vector that corresponds to differential of a function, and the correspondence is defined by scalar product. If I have a scalar product on a vector space, I can associate to the scalar product a certain map acting from vector space to the dual. The dual are linear maps from the vector space to R. I will denote this map by capital G. Capital G acting on a vector is such a covector that I get placing a vector in the first place of the scalar product, or second place because scalar product is symmetric. Since here is an empty thing, an empty space waiting for a vector, it means that this is a linear map from V to R, therefore an element of V star. So what's the gradient? My differentials of functions live here. So if I need a gradient of f at point P, or we sometimes write it like that, or we sometimes write it like that, I need to take the differential and apply g to the minus 1. To the minus 1 because I want to act from here to here. And the scalar product is non-degenerate, which means that I can take this inverse. This is the definition. And now we can write this definition in different bases. One basis will be the orthonormal basis associated to Cartesian coordinates, and another will be basis, this one, associated to the operation of differentiation. And the result that we get here will be what is called gradient in polar coordinates. So we will not be changing coordinates from Cartesian to polar, but we will be realizing this definition. We will be realizing this definition in different coordinate system. For that, we need matrices. We have matrices of the differential written in two different coordinate systems. We have for that matrix in Cartesian coordinates, which is df, dx, df, dy, and we have another written in polar coordinates, dr, d phi, and this is df, dr, df d phi. Now we need a matrix of this map G inverse written in those two bases. So now this is a pure algebraic problem, how to write a matrix of such a map. We have to recall all the knowledge we have about symmetric bilinear forms and the matrices of symmetric bilinear forms, because this matrix is precisely the matrix of scalar product, inverted, of course. Inverted matrix of a scalar product. How do we get it? If I have a scalar product and I have a basis, for example this one, I can get a matrix taking scalar products of matrix elements. It will be, of course, a symmetric matrix because scalar product is symmetric. And since basis E is orthonormal, then these products are 0, these are 1. So the matrix is very simple. However, if I do the same for the R d phi, I get that since dr and d phi are orthogonal, here I get 0. Here I have 1 because the length of dr is 1. However, here I have r square because the length of dr is equal to the length of d phi is equal to r. So the matrix is as follows. This is a matrix. Those two matrices are matrices of a scalar product of the scalar product in two different bases. This is the same matrix as for G, but here we act from the vector space using basis E to the dual vector space using some basis which is dual to E. And here we do the same. We have the same operator, but here we start from dr d phi and land in the basis that I will denote like that for some reason. But what it is the dual basis for the dual for this one. Okay, so having those matrices, I can finally write a gradient, the gradient. Let me look from above. What do I have to do? I have to apply the matrix to the inverse matrix. I have to apply the inverse matrix to a vector, a covector. So in blue, I work in Cartesian coordinates. G to the -1 corresponds to the identity matrix in Cartesian coordinates because G was the identity matrix. And I act with this matrix on this vector and of course I get this vector, and this is my gradient vector as a vector written in basis E. So it is df over dx ex plus df over dx e phi. In yellow, I do the same for polar coordinates. I act with the inverse matrix, which is in this case 1 in one corner and 1 over r2 r square in the second corner. I act on differentials. Sorry, one should keep the order correct. Here is r, here is phi, and what I get is df dr df d phi multiplied by 1 over r square. So my gradient in polar coordinates is df dr dr plus df d phi 1 over r square d phi. So this is the gradient in polar coordinates. Of course, this is not what you see when you look in the internet or in the book for the gradient in polar coordinates, because what you see there is the following formula. Because in the internet or in the book you usually find the expression written in orthonormal basis. The basis composed of those differentials is orthogonal but not orthonormal. The basis composed of those vectors is orthonormal, and the correspondence between g phi and d phi is precisely by 1 over r square. So I borrow 1 over r from here, join to this, and I get gf. I can write it down like that. This is df dr gr, because dr and gr are the same, plus 1 over r df d phi 1 over r d phi, and this are the same. So finally I got the correct formula, and now you are ready to write a gradient in whatever coordinate system you need. You just take your function, say on Rn, differentiate with respect to whatever strange coordinate system you want to use. You write a matrix of a scalar product in this strange coordinate system. So this is the matrix which is composed of elements dy1 I multiplied by dyj. Yeah, you take the inverse of this matrix and you apply to the vector composed of that. And what you get is a gradient written in the basis composed of precisely those vectors.